Good morning. I'm Ranjani from Professor Jeremy Levy's group in the University of Pittsburgh. My topic is Magnetotransport properties of LaOSTO-based ultra-dense two-dimensional nanowire networks. In this talk, I'm going to talk about how to create a bunch of nanowires on the LaOSTO interface and create tunable coupling between the wires. We can use this as a model system to simulate different quantum electronic behavior. Correlated electrons show a lot of interesting properties like ferroelasticity, ferromagnetism, superconductivity, etc. It is difficult to study such properties because we have to probe things at an electronic length scale of few nanometers. So it is always an interesting area of research to find mesoscopic model systems that can show the similar behavior at slightly bigger length scales. For example, ion traps are used to trap ions at specific lattice sites to simulate any atomic lattice. Cold atoms have been used and suggested as a Hubbard model simulator. Rydberg atoms are used to study antiferromagnetic lattices. The ability to control and fine-tune the model system is an important challenge towards this application. In our group, we use the LaOSTO heterostructures as the model system. This structure is very interesting because it hosts a high mobility 2D electron gas at the interface between LaO and STO. It has been shown that at a critical thickness of 3 unit cells of LaO, there is a metal-insulator transition in the system. The system can be tuned from insulating state to a conducting state by techniques such as Conductive AFM lithography and electron beam lithography. There are also other interesting properties shown by this system like superconductivity, magnetism, and tunable spin-orbit coupling. We use ultra-low voltage EBL to pattern our devices. More details about this technique are given in this reference. In this technique, we expose the interested regions of the sample to an electron beam. This causes protonation of the surface. This in turn leads to electron accumulation at the interface, making that region of the sample as a conducting region. This entire process is done under vacuum to ensure minimal decay to the sample. We can also write through thin van der Waals layers like graphene, boron nitride, etc. We can reach a resolution of up to 10 nanometers at room temperature using this technique, and it is also much faster than the previously used technique of Conductive AFM lithography. We have electrical feed through that allows us to measure the electrical properties and see the conductance jumps without breaking the vacuum. The device here is a collection of horizontal nanowires of length 38 micrometers. D represents the spacing between the wires. At room temperature, we monitor the conductance along two directions. S and D stand for source and drain, and the first figure shows the voltage measured parallel to the direction of wire and the conductance is labeled G parallel. Similarly, along the vertical we have G perpendicular. We expose a series of interleaved lines layered by layer to change the spacing. For example, we first expose the collection of green lines shown over here with a spacing of 2 micrometers, and then we measure the conductance along parallel and perpendicular direction. Now to the same device we expose another set of red lines which makes the overall effective spacing 1 micrometers. Now we measure the conductance again on both directions. We keep going till we get some conductance along the perpendicular direction, which indicates that the wires are coupled now. This plot shows that at 250 nanometer interwire spacing, the conductance along parallel and perpendicular are of the same order, which is a few microsievens. The device with the 250 nanometer interwire spacing was transferred into a dilution fridge with a base temperature of 20 millikelvin for low temperature characterization. At this temperature, LaOSTO has superconducting properties. We first apply a magnetic field of 1 Tesla to study the normal state behavior. The top figure shows that G parallel is 0 until 1.7 volts, so the device is insulating, and above that voltage of backgate, the conductance increases gradually along the parallel direction. This behavior is shown by nanowires and is expected. However, G perpendicular in the conducting region shows a barrier, and the width of barrier keeps decreasing with increase in backgate voltage. This indicates that we have a backgate tunable coupling between the wires. We turn off the magnetic field to study the superconducting behavior. This slide talks about the horizontal configuration. In this graph, we see the appearance of a new feature, which is a peak in conductance at zero bias, which was not present in the previous slide. A line cut along 50 volts of backgate shows that this conductance jump is around 60 microsiemens. Plotting this as resistance versus current, we see that the critical current of the sample is around 100 nanoamps. This behavior of resistance not dropping all the way to zero in the superconducting state has been observed previously in LaOSTO heterostructures. These are some of the references where they observe a few kiloohms of drop in resistance at the superconducting state instead of a zero residual resistance. This is explained by the hypothesis that there are puddles of superconducting state interspersed with normal states in this large-scale sample. Along the vertical direction, the figure shows that we see a barrier until 48.5 volts of backgate. Above the barrier, we see the same superconductivity at the zero bias. And on increasing the backgate further, we see that the superconductivity persists. The line cut of resistance versus current shows us the critical current is still around 100 nanoamps. This shows that the superconducting behavior is also coupled in the direction perpendicular to the wires. Now we apply a magnetic field perpendicular to the sample surface. The top graph shows that R parallel is higher at higher magnitude of magnetic fields and is lower in the absence of field. This is expected from nanowires on LaOSTO. However, along the perpendicular direction, we see that R perpendicular is several mega ohms at plus minus 18 Tesla and goes down till 2 kilo ohms at 0 Tesla. This indicates that we have a metal-insulator transition on application of magnetic field, and this transition is reversible and non-hysteretic way to tune the coupling between the wires. This device can act as a model system to study stripe phase superconductivity. In cuprates, the antiferromagnetic interactions compete with Coulomb repulsion, leading to regions of high dopant concentration that form stripe-like structures as shown in this figure. So this phenomena is better modeled as a series of conducting stripes on an insulating background. We can also use it to study quasi-1D chains. Some chalcogen-based compounds act as quasi-1D chains with weak interactions between the chains. We can also use this device to study the dimensionality crossover, where some models predict a quantum confinement phase transition and interesting properties as we transition from 1 dimensions to 2 dimension with fine-tunable parameters. We have shown that we can make a series of nanowires at the LaOSTO interface using ultra-low voltage EBL. The coupling between the wires can be tuned using a backgate voltage. Superconducting properties are also coupled in the direction perpendicular to the wires. We observe a magnetic field-driven metal-insulator transition. This can act as a stepping stone to making a model system that simulates the high temperature stripe phase in cuprate superconductors. Thank you.